I have two quick announcements before we begin with class. One announcement is that there's a homework number 7 that's posted on the Blackboard now. And I made that due on Tuesday of next week, December 8th. I'm sorry, that's a short deadline, but it's a short homework assignment. And it's based on what I'm going to talk about in the class today. And the other announcement is about the final exam. Okay, so based on Kent State's exam schedule, the official date for the exam is Monday, December 14th at 10:15 to 12:30. Now, I'm willing to give you guys more time than this. I'm willing to give you guys 24 hours, the same as for the midterm. I think that worked out all right, as far as I know, for the midterm. I don't really care which 24-hour period. Maybe it would be good to have a 24-hour period that includes the exam period so that if anyone asks, I can tell them I took the exam period and just extended it. Do you guys have any conflicts that would be problems? That is anything else with any of your other classes around that time? Okay, then how about Monday at 10:15 till Tuesday at 10:15? Okay, so starting at the official time, but I'll just give you 24 hours to work on it. Does that seem all right to you guys? Okay, so I'll keep that. Okay, so I'll say Monday, December 14, 10:15 a.m. until Tuesday, December 15 at 10:15 a.m. Okay, that is the final. And on the Blackboard, I posted several old final exams from past years, which you can look at as part of your preparation if you want to. Maybe I'll use a similar style, maybe I won't, I haven't written it yet, but this way everybody can look at the old ones and have the same preparation. Okay, we good for practical things? Any practical questions? No. All right then. So the subject that I want to talk about today is another thing related to non-uniform director fields. Okay, so in the last class, we talked about the Fredericks transition. And I guess one way to think about that is that this is a small distortion in the director field. So N of R, and it can come and go. So as you adjust the electric field or the magnetic field, then you could have a uniform state, or if you turn up the field, then you get a little bit of a distortion. If you turn up the field some more, you get a bigger distortion. If you turn off the field, it goes back to uniform. Now, let's think about a different kind of distortion. Let's think about defects. And the point of a defect is that these are large localized distortions in the director field, which cannot come and go. These are distortions that are stuck in the liquid crystal. They are metastable, you might say, in the liquid crystal, so that you can't make any small change in the liquid crystal to add or remove defects. And instead, it requires much larger kinds of changes. Okay. Now, there are several reasons why defects are important as part of the study of liquid crystals, or indeed the study of any subject in material science. And so just to list some reasons why these things are important. One is they help us to recognize phases. So each kind of phase has its own sort of defects. And so if you get used to what kinds of defects are in a phase, it helps you to know what is you're looking at under the microscope. And indeed, sometimes the people who know the most about what defects look like are chemists who are not especially interested in defects themselves, but they just look through the microscope a lot and they want to know what different phases look like. And so they just get a practical knowledge of what defects look like in different phases. Another reason in general in material science why defects are important has to do with different properties of the material. Many kinds of properties like mechanical properties or transport properties are controlled by the microscopic structure of a material, which especially means the presence or absence of defects. And in many cases, if we want to build liquid crystal devices, we want to eliminate defects for applications. We don't want a defect, in the middle of a liquid crystal display, for example. Though they are, in fact, useful for certain applications, especially things that involve bistability. That is, if you want to have more than one stable configuration of your device. Okay, so that's an introduction to why people study the subject of defects. Let's look at some specific examples to make this all more concrete. Okay, so to think about specific examples, I want to concentrate on 2 dimensions instead of 3 dimensions, because this subject is really much easier in 2 dimensions than 3. And let's begin by talking about a polar phase rather than a nematic phase. So a polar phase is one where the molecules tend to be pointing mostly in one direction. So there's some average vector, as you know from the homework assignment. Right? And so it's different from a nematic phase where they're pointing in a direction or the opposite direction. Okay, so in a 2-dimensional polar phase, the orientation is described by an arrow. So like these arrows, right? Meaning that that's the local average direction of polar order. Right? So you can imagine each of these blue arrows is a local average of thousands and thousands of little molecules, which are all pointing in different directions, but they have an average locally that's represented by the blue arrow. So this blue arrow is a vector in 2 dimensions. It has a characteristic magnitude, which is based on what's this favorable strength of polar order. Let's represent it by a unit vector. So we'll divide out the magnitude. Okay, and so we'll say there is a unit vector p hat as a function of position r. And since it's a unit vector, we could write it as the cosine of some angle phi of r, and then the sine of some angle phi of r. Okay, where phi of r is the angle away from the x-axis. Now, this P might be uniform, right? It might point in the same direction everywhere. Or it might have just small distortions. It might have something like this, where it's not pointing in the same direction everywhere, but there's a small distortion, and you could make small changes to these vectors to force it to be uniform. Okay? But now, consider the structure that's in this picture over here. Right? This is a more complicated kind of thing. Right? This is a configuration where the orientation is going around in a full circle as you go around this central point. Right? This structure is a defect. Okay, so this is one example of what could be called a defect, or another word people could use would be a vortex or a disclination in the polar order. Okay, and so you could see, there's no simple way to make this thing be uniform. If you try to force some of these directors to point in the X direction, well, it'll just be frustrated somewhere, right? You could try rotating around, this guy. You could rotate around this guy to point that way, and this guy, but that would just make the defect move. It wouldn't get rid of the defect. Okay, if you tried to get rid of the defect, the only way you could do it would be to keep moving it until it went all the way off the edge of the sample. Right? There would be no way to make just some little changes to get rid of it. You'd have to push it all the way to the edge. Okay. Now, we can see that the defect is there. There is a mathematical construction to identify that there's a defect there and identify what type of defect it is. Okay, and that kind of construction is called a Berger's circuit. So the idea here is that if we want to know whether there is a defect inside some region, then we draw a loop around that region. Okay, and so in this illustration, I drew a red circle. A red circle that is here. Okay, and I want to know, is there a defect inside that circle. The way to figure that out is to pick a starting point, like how about here, right? And then let's go around the circle in a counterclockwise way, conventionally, and let's track what happens to the angle phi, this angle, as we go around the circle. Okay. So here, we could say, well, phi equals 0. Then up here, phi equals pi over 4 radians. That corresponds to 45 degrees. Okay. And then if we keep going up to the top, we get to phi equals pi over 2 radians, 90 degrees. If we keep going around, we get to phi equals pi, 180 degrees. Down here on the bottom, we get to phi equals 3 pi over 2. That is 270 degrees. And if we keep going around, we get to phi equals 2 pi when we're back at the starting point. Okay. So we can see we've gone around this path back to the same place where we started, but the angle phi is different from what it was at the beginning. Now, the p is still the same. The vector p is the same because the sine of 2 pi or the cosine of 2 pi, it's the same thing as the sine or cosine of 0. Okay. So it's the same p vector, but it's a different angle phi. Okay. If we go through and make all these little continuous changes in phi, going around from point to point to point to point, right? Looping about there. So this is written as an integral. Okay. So people would say, let's make an integral around the loop, adding up all the little changes in phi. So the integral around the loop of d phi. And in this case, the sum of all those changes is 2 pi, right? That we've changed from starting at 0, going up to 2 pi. So this integral is 2 pi. In general, the definition of the topological charge is based on a loop like this. We'll say that the integral d phi about the loop is 2 pi times the topological charge that is enclosed by the loop. Right? So this tells us that the red loop that I drew there encloses a total topological charge of +1. So this example, it's 2 pi times +1. So we would say that there must be a total topological charge of +1 inside the loop somewhere. Now, where is it? Well, we could try shrinking the loop. We could say, let's make a loop around there. Yep, charge is still in there, okay? What about a loop around here? Nope, there's no topological charge inside of that loop. That is, if you track phi going around this loop, it increases, 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 and then it decreases, and it comes back to where it started. Okay. Or the same over here. If we track phi going around this loop, increase, 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 nope, no, decrease, 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 and it comes back to where it started, okay? So that the integral d phi is 0. This is a construction which is similar to Gauss's law from electrostatics. Okay, so you remember in your electrostatics courses, right, that if you want to know if there's an electrical charge inside some region, right, you can make a Gaussian surface around the region and calculate properties of what's happening on the surface. And that tells you the electric charge that's enclosed. Related kind of thing here, right? That the behavior on the surface tells us about what's enclosed by the surface. And so that's, you know, an analogy which would lead us to call this thing a topological charge, right? But that's an analogy. It's not really an electrical charge, right? There's nothing electrical about this. Okay, now, if you are thinking about that analogy, let's now look at a picture like this one. Okay, so this is a trick picture because whenever I show it to students, they immediately say, oh, well, this must be the charge of -1 because, you know, it looks like the electric field around the opposite sign of a point charge. In fact, that's not true. Okay, so let's figure out the topological charge of this using the same construction. Okay, so here we'd say this thing starts at phi equals pi. Okay. And now if we go up this way, we get to a bigger phi. So up here, it is phi equals 3 pi over 2. And then if we go around here, it keeps on increasing and we get to phi equals 2 pi. And then it keeps on increasing. And down on the bottom, it's phi equals 5 pi over 2. And then we keep on going up here, it's phi equals 3 pi. Okay. So if we look at the whole integral around the loop, that is, you know, the ending value, 3 pi minus the beginning value, pi. So that's 2 pi. So the enclosed topological charge is equal to +1, right? So it's different from what you would guess. This is not -1. So the analogy with Gauss's law is interesting, but it can be misleading. And so you have to watch out for that, okay? So these are two different forms of defects with a topological charge of +1. Okay. What else could we have? Well, let's look at this picture here on the left. Okay. In this picture, we start off with phi equals pi over 2. Okay. Then it keeps on increasing. Up here, it's phi equals pi. Keeps on increasing. We get to phi equals 3 pi over 2. Then phi equals 2 pi. Then phi equals 5 pi over 2. So the integral here, d phi, that's the ending value, 5 pi over 2 minus pi over 2. So this is 2 pi again. Okay, so the enclosed charge is +1 again. When I'm doing this, you know, by myself, I take the Apple Pencil or any kind of pointing thing, and I just rotate it around going about the loop. And that helps a lot. I can see which way the pencil turns as I go about the loop. Unfortunately, I don't have a good high-tech way to do that. That's a low-tech thing to do, but it actually works very well. And so I recommend doing that. The same thing works for the picture on the right. That this is another example where the integral d phi is equal to 2 pi. And so the enclosed topological charge is +1. So these things that I've shown you so far are all examples of defects with a topological charge of +1. Okay. So now you're wondering, these things are all examples of +1. How do you get a -1? Well, I'll show you. Okay, let's look at this example here on the left. Okay, so over here, let's again go around the loop and see what happens to the director. Okay. So it starts with phi equals 0. Okay, the director is pointing to the right. Right. Now, as we go up here, the director is rotating in the opposite way. Okay, and so instead of going to bigger values of phi, it's going to smaller values of phi. Okay. So this is now phi equals negative pi over 2. As we keep going around, we get to phi equals negative pi. We keep going around, we get to phi equals negative 3 pi over 2. And then around to the beginning, we get to phi equals negative 2 pi. Okay. So phi has gone around in a negative way, okay, from 0 to negative 2 pi instead of 0 to positive 2 pi. So this is an example where the integral d phi is negative 2 pi, the ending point, minus 0, the beginning point. So it's negative 2 pi. That means that the enclosed charge is equal to negative 1. So this is an example that shows a negative topological defect, negative 1 topological defect. Okay, so that means in some sense, this defect is the anti-defect of the first thing that I showed you. Right? So if these things are anti-defects of each other, then their effects on the director field should cancel. Okay? So let's see this example now on the right. Over here on the right, on this side, this looks like a +1, right? The director is pointing outwards from this point everywhere, right? And we figured out that that's a +1. Okay? So I'll say +1 there. And by comparison, over on the left part over here, this is a -1, right? Here the director is sticking outwards in 2 directions and inwards in 2 directions, just like the thing I analyzed over there. Okay? So this is a -1. So if I go around the loop here, I see the integral d phi is equal to 2 pi. If I go around the loop here, the integral is negative 2 pi. Okay. What if I go around a great big loop that includes both of them? All right, let's try it. Okay, so over here, we start at phi equals 0. And then as we go along, phi is increasing, increasing, increasing. Here it gets to phi equals pi over 2. Now, as we keep going, it's decreasing, decreasing, decreasing. So here it's phi equals 0. Now I'll keep going. It's decreasing, decreasing, decreasing. And we get to phi equals negative pi over 2. Then it increases some more, and it gets back to phi equals 0. So for the big loop, the integral d phi is equal to 0. Okay? So the topological charge that's enclosed by the big loop is 0. Okay? So there's a +1 and a -1, and they add up to 0. So that is an example of the cancellation of two opposite topological charges, a positive and negative. Okay. Let me show you a really cool movie if I can. Let me see if I can switch to Mathematica briefly. Let's see, right over here. So Mathematica. Here. Okay, so over here, you see this picture, right? Yes, good. Okay, so this is a +1 defect there, a -1 defect there. Now I can actually let them move. Okay, so here, they're gradually moving towards each other. And they come together and they annihilate each other. So this is the liquid crystal analog of an electron annihilating a positron, that sort of thing, right? So a defect and an anti-defect, which annihilate and make a nice uniform defect-free configuration. Let's go back to the whiteboard.
Question.
Please.
So I assume for different materials, there might be some where they're so fragile, like their structures put together are so fragile that maybe defects, if they're close enough, would annihilate each other compared to other materials. Is that related to like stress and strain properties of a given material, of whether how close their defects can get before it'll kind of forcefully shuffle down and annihilate each other?
Yeah, your question is related to defects in solid materials, okay, which is actually a very big subject. And in solids, in crystalline solids, there definitely are defects. They are a little bit different from defects in liquid crystals. The main kind of defect in solids is called dislocations. Dislocations are indeed extremely important for the strength of materials. That's sort of what you're asking about. That is a big part of what material scientists study. It's a little bit different from what I'm talking about right now in liquid crystals. And so I think I'm going to have to defer that question in general. Okay, Chris, let's maybe talk about that separately.
Thank you.
All right, sorry. So coming back to the liquid crystals, just briefly, well, in liquid crystal, this is still in the polar phase, in the 2D polar phase. Over on the left, this is an example of a charge of +2, which you could tell by following what happens to the director as you go around this loop. And it goes all the way from 0 to 2 pi, and it keeps on going up to 4 pi. And here it rotates in the opposite way. So this is going from 0 around to -2 pi, and then -4 pi. So this is a total charge of -2 right there. Okay, so this is the story about a 2D polar phase. But as we've discussed in liquid crystals, we normally don't have a polar phase. We normally have a nematic phase instead. And nematic order is not represented by an arrow with one head, right? A nematic order is represented by an arrow with two heads, right? Indicating that n and negative n are equivalent to each other. Or it could be represented by an arrow with no heads, just a little line segment. So what can we get for defects here in a 2D nematic phase? Okay. First of all, you can get the same sorts of things that occur in a polar phase, right? So this on the left is an example of a charge Q equals +1, right? The same as what I showed you previously in the polar case. This is also an example of Q equals +1, right? These are two cases where the director rotates around from 0 to 2 pi, or pi over 2 to 2.5 pi, as you go around the loop. Okay, but in a 2D nematic phase, unlike a polar phase, you can also get other kinds of defects, right? Here, there are extra types of defects that can occur in a nematic phase. This picture on the left, let's figure out what kind of charge is associated with that. So here, we start at phi equals 0. And now, as we go up to the top, we rotate up to phi equals pi over 4, 45 degrees. Okay. We keep going around. Here, we rotate to phi equals pi over 2, 90 degrees. We keep going around there, and we get to phi equals 3 pi over 4, right? That's 135. And then we keep going up here, and we get to phi equals pi. So that means that the integral d phi is pi minus 0. It's pi. Okay. So that means that the enclosed charge is plus 1/2. Okay. So the nematic phase can have a charge of plus 1/2, which is not possible in the polar phase. Okay. Why is it not possible in the polar phase? Well, suppose we tried to make a charge of plus 1/2 in a polar phase. We would have a director that, or a polar vector that starts like this. And then we keep going up and it would look like this. And around here, it would look like that. And here, it would look like that. And here, it would look like that. And we'd say, uh-oh, we've got a big problem here, right? Because we've gone around the loop and P has changed, right? There wouldn't be a well-defined P everywhere, right? Because here we would say P is in the plus X direction, but P is in the minus X direction, okay? So this is no good, right? And so this is forbidden in a polar phase. But in a nematic phase, no problem, okay? Because the n is equivalent to negative n, okay? And so if you start with some n over at one side of the loop, and you go around, and you get to negative n, no problem, because n and negative n are equivalent to each other anyway, right? Or the arrows are double-headed arrows anyway. So it doesn't matter if you change the arrow pointing one way to the arrow pointing the opposite way. So this is the structure that is a plus half defect, okay? What about a minus half defect? That is what's shown in the picture on the right. Okay. So here we could say, let's start with phi equals 0. And now as we go up this way, we are rotating phi in a negative sense. So we get up to phi equals negative pi over 4. And then we keep rotating in a negative sense. So here is phi is negative pi over 2, so negative 90 degrees. And then we keep rotating in a negative sense down to phi equals negative, whatever it is, 3 pi over 4. And then around here, phi equals negative pi. So the integral d phi, that's negative pi at the end minus 0. So negative pi. So Q enclosed is equal to negative a half. This is another structure that would be forbidden in a polar phase for the same kind of reason as down there, right? That if you were to try to do this in a polar phase, you'd go around the whole circle and the P would point the wrong way, it would be pointing the opposite way. So it wouldn't come back to the same P where you started. Right? But for a nematic phase, no problem, because n and negative n are equivalent to each other. Okay? So in general, then, the rule is that in a polar phase, the charge must be an integer. But for a nematic phase, the charge must be an integer or a half integer. And indeed, the half integers are the common thing. The integers are not common. Okay, the half integers would be common. Let's see. So here I have a couple examples of higher charges. And with each of these cases, it's good to track, using a pencil or some kind of pointing device, right? To follow around the loop and see how many times you turn your pencil, okay? And if you do that, then you will see that this is a charge of plus 3/2. And this one is a charge of negative 3/2. Okay. Now, what about adding these things together? That works also, okay? So here in this example, here we have a defect of plus 1/2, right, at this point. You can see it has the same kind of shape that we saw for the previous plus 1/2, right? It's a shape that looks, you know, sort of like a comet, right? Where it's curving around like that. People call that a comet sometimes, right? And over here, we have a defect with a topological charge of negative 1/2. And now, if you draw a great big loop that includes both of them, then you get from, let's see, phi equals 0 up to 45 degrees, pi over 4, and then it rotates here back down to 0. And then it rotates here to negative pi over 4, and back here to 0. Okay? So this is a Q enclosed equals 0. By comparison, the picture on the right shows 2 defects of plus 1/2 each. Plus 1/2 and plus 1/2. And if we go around this full loop, well, we go from phi equals 0, phi equals pi over 2, phi equals pi, phi equals 3 pi over 2, phi equals 2 pi. So as we go around this loop, we see a change of 2 pi, which means that the enclosed charge is equal to plus 1, just plus 1/2, plus 1/2. Okay, so that all kind of makes sense. In the new homework that I just gave you, I am showing a lot of different examples of two-dimensional pneumatic textures like this. And I'm asking you to tell me, you know, which ones have defects and which ones don't have defects. And if there are defects, to figure out what the topological charges associated with the defects might be. So this is a homework which, you know, I hope will be a little bit fun like this, ha ha ha. And, but you know, it's not homework that involves calculations. It's homework that is looking at these pictures and doing the topological constructions like this. I should say, let me close for today with a couple of other points, okay, just briefly. One is that the kind of mathematics that I'm showing you here, where we draw loops and count how many times things rotate. Right? This is a branch of mathematics called topology. Right? It's like geometry, but we're not really measuring things that could have any continuous value. Instead, we're counting things, right? And so topology involves this concept of counting, things that could be just integers, or perhaps just integers or half integers, right? But either way, it's things that you count as opposed to things that vary continuously, that can be any continuous value. Okay? And that goes along with the idea that these defects are stuck, right? That you can't make small changes that will get rid of the defects, okay? Because the defects are characterized by a topological charge, which has to be an integer, or perhaps an integer or half integer. Right? And if something is stuck, say, at a half integer of +1, you can't make any little continuous changes to change +1 to 0, right? Because you can't go smoothly +1, +0.9, +0.8, +0.7, right? Instead, you have to go all the way from +1 to 0, right? And so that is a special feature of these structures. And so these things are often called topological defects. This is a big subject in physics and was honored with the Nobel Prize just a few years ago. And so indeed, researchers in many areas of physics are interested in this kind of thing, of topology, topological defects, topological materials. One other general point is, I was showing you the easy version of this subject, which is in 2 dimensions. In 3 dimensions, it's harder, okay? In 3 dimensions, that is, if the director can be 3-dimensional, then the way that you characterize defects is more complicated in a few ways, right? One way that it's more complicated is that you have to distinguish between line defects versus point defects. So you could have a point in 3 dimensions, which is enclosed by a surface. A point, and I'm drawing a whole sphere around it, right? And this is enclosed by a surface. Or you could have a line defect, which is enclosed by a loop. And these things each have their own topological classification, right? So in 3-dimensional materials, you have to think about both of these things, not just one. There are further complications that I can't even get into quite here, but I will just say in 3 dimensions, the addition of topological charges doesn't work. That is, in 2D, the topological charge, it just adds up, right? And so we can add up the plus halves and the minus halves and you get 0, things like that. But in 3 dimensions, for more complicated mathematical reasons, it doesn't work. And so, 2 plus halves can add up to make 0 in the 3-dimensional counting. I'm just making you aware of that, right? That there is the greater complexity. Hang on just a second. That there is this greater complexity, and it's a really interesting subject, but I'm running out of semester and I'm not going to be able to talk about that. For people who are interested in these three-dimensional issues, I especially recommend the textbook by Maurice Clayman and Oleg Brintovich, which really goes into the three-dimensional aspects in great detail. Okay, so that's what I wanted to say about the topology, and that gives you the information that you need for the homework. On Monday, I'm going to talk about energy associated with defects. But for now, I'll be glad to answer any questions. And Vijaya, I know you had something, so please go ahead.
So if I have a liquid crystal cell with a few nanometer thickness, then can I apply these 2D defects or not?
The question is whether the director is free to change as a function of the going across the thickness, right? And so, well, excuse me, there are two questions. One question is whether the director is free to change as a function of Z, right? So if it is extremely narrow, if it's just nanometers difference from the top to the bottom, then probably the director can't change in there. And so that is two-dimensional. That's one question. The other question is whether the director has to be in the two-dimensional plane, or if the director is free to point in any direction in three-dimensional space. So that is to say, if you have n of r, one thing is, is the n 2D or 3D? And the other question is the r 2D or 3D? And both of those questions are important. Okay. The issue about line defects versus point defects, that mostly has to do with is the R 2D or 3D? And the issue about addition of topological charges, that mostly has to do with is the N 2D or 3D.
And let's assume in olive groups, they can create these topological charges by patterning electrodes. And if they are creating topological charges by patterning electrodes, then I don't think we can apply this addition rule of topological charges, because these topological charges are not moving.
Well, they don't have to move in order to be able to apply a rule.
No, I mean, let's assume we have two topological charges. We have two defect or different topological charges on liquid crystal cells. They are going to combine. Am I right?
If they are free to move, then they
Yes.
will they'll be attracted together, and that's what I'll calculate on Monday, and then they will tend to combine. Yes.
And but if we are creating topological charges by patterning electrode, then they cannot combine. They cannot move.
Well, sure, but they still are there. You can still calculate topological charges mathematically.
Yes.
by looking at how the director varies as you go around them. And so you can still do this kind of analysis. It's just that they're not mobile. Right?
And what are the other ways to create these defects without patterning electrodes?
Well, one way is when you cool an isotropic phase into a nematic phase, say by rapidly reducing the temperature, it will not make a perfect nematic phase. Right? Normally, it will make a nematic phase with a lot of defects. And so that happens because there are different regions. And in one region, the liquid crystal order will be oriented this way, and in another region, it will be oriented that way. And then when the regions come together, there will be some kind of defects at the interfaces. So
But
normally,
okay.
those things will annihilate each other pretty quickly after the material is created. And so those will be sort of temporary defects.
But I cannot create a defect of particular kind by that way. Let's assume I mean I cannot create +1 defect or -2 defect by cooling. They can be of any kind. Am I right?
Yeah, it's not under your control, right? It just happens all by itself. That's correct. So if you want to control it and make just the sort of defect that you like, yeah, patterning the boundary conditions is a very good approach for that. Right? So patterning, well, it could be electrodes or any other kinds of anchoring surfaces. That is a very good way to control what's happening for the director configuration.
Okay.
So there are several groups at LCI that do that sort of work.
I have a question. You showed to us that there are 3 different kind of defects where all of them have +1 topological defect, right? The topological charge of them are +1. And you also showed us that there are 2 different kind of constructions where both of them have +1 in pneumatics. Both of them have +1 topological charge. So my question is, can I always get one from another by doing continuous transformation?
Yeah, so it's not just 2 or 3 possibilities. There's a whole continuous family of possibilities.
Right.
So the director could be pointing out everywhere, right? Or the director could be pointing in everywhere. Those are different in the polar case, they're the same in the pneumatic case, right? Or the director could be pointing tangentially everywhere, like that, right? Or it could be anything in between. The director could be pointing at any intermediate angle between those 2 extremes. And I think I had one example of that way back at the beginning on the right here. This example, right? This is an example where the polar vector is pointing at about 45 degrees compared to the radial direction everywhere. So yes, you can go continuously from the radial sort of defect to the tangential defect through intermediate configurations like this.
Okay. So what is the difference between them? So in liquid crystal, which configuration is the stablest?
Okay, so if we go back to these 2 possibilities in the pneumatic, right? So this is the radial one, this is the tangential one, and there are also the intermediate ones, as I just said, okay? So if you compare these 2, one big difference is that the director in this case is all splay.
Right.
And the director in this case is all bend. Okay. So if we have the simplest version of the Frank free energy, where the elastic constants for splay and bend are equal, then these 2 things have equal energy.
Mm-hmm. Right.
And the states in between them will have equal energy. So right. You could go continuously from one to the other, right? However, In most experiments, the splay and bend elastic constants are not the same. Right? And so the more stable defect will be whichever of those things has a smaller elastic constant. Because you can't get rid of the defect completely, but you can change splay to bend or bend to splay continuously. Okay. And so if you let the material relax, it will change to whatever is the lower free energy. So it'll be all bend or all splay typically.
Okay, so the configuration of the topological charge is decided by the elastic constants, right?
Yes, yes. That in realistic systems with unequal elastic constants. Yes, that's absolutely right.